Hello, and welcome to Aggressive Physics. Today is day 91, and I'd like to talk about the law of reflection. Now remember, light is an electromagnetic wave, and it can travel through the vacuum of space. But what we haven't talked about yet is how we see objects. Now there's two ways that we can see an object. One is if it's the source of the light. For example, a light bulb is emitting light, the sun is emitting light. So we can see those objects because light is coming from them, and we absorb that light into our eyes. Now other objects need to have light reflected off of them. And what happens is the light will hit the object, bounce off, and go into our eyes. The light is absorbed by our eyes, and we can see the object in that case. So in order to actually view an object, there needs to be light reflected from it. That's why it's difficult to see mirrors or possibly glass windows that are really clean. If we have a glass window that's really clean, a lot of times you'll hear about birds running into them. Well, the reason they run into them is because they don't reflect light as well, and most of the light is passing through. Remember, every time a wave hits a boundary, three things happen: reflection, refraction, and absorption. So the reflection shows the object and the fact that it's there. A really clean window will not reflect as much light. And what happens is people or animals will not see that and sometimes bang right into them. When we see the color of the light, that's the light that's reflected off of an object. So if an object's green, that means it's reflecting the green light and absorbing other lights. So the color of the object is determined by what light is reflected from it. Light that is absorbed into it is not reflected, so therefore we don't see that color. So if you're wearing a certain color shirt, that shirt is reflecting that color light and absorbing the rest. Now, when light reflects off of something, it bounces off at the same angle, and that is what we call the law of reflection. It's based on what we call Fermat's principle. Now, what Fermat said is that light is going to travel in the path that takes the least amount of time. So light travels in straight lines, and our eyes know that. So instinctively, we know that light travels in straight lines, and what happens is we're going to extend back along that straight line all the light rays that go into our eyes, and that will form an image in our brain. Now, when that happens, we can view an object in a mirror or in real life as looking to be in the same spot, and that's because our brain knows that light's going to travel in a straight line backwards. The intersection of all the rays of light are where the object occurs. Now, with the law of reflection, we have an equation, and it's theta I equals theta R. I is for incidence, and that means incoming light ray. R is for reflected, and that's the outgoing light ray. Now, the angle is measured from a normal line. So what we're going to do is take a line and draw it perpendicular to the surface and measure the angle of the light ray from that normal line. The reason we do that is because not all surfaces are flat. Microscopically, even an object that may appear very flat is really quite bumpy. And when the light reflects off of it, if we were to draw a normal line, it would be difficult in anything other than a completely flat surface. So by default, we use a normal line, which even on a curved surface or a bumpy surface is a little easier to see, and we measure the light rays from that. So the law of reflection is angle of incidence equals angle of reflection, and that's based on Fermat's principle. Now, a mirror is typically what we'll use to bounce light off of, and a lot of times in a physics class we'll use lasers. Now, when the light comes down, it'll hit the mirror and bounce off. Instead of measuring the angle from the mirror's surface, we need to remember that the light is always going to be measured and the angles will always be measured from normal lines. So we need to draw that line vertically if we have a horizontal plane and then measure the angle from that. Many tricks on the Regents exam or other assessments give angles from the surface, and we need to find the complement of that in order to determine the law of the angle of incidence or reflection. But simply stated, the angle going in is going to equal the angle out. And there's a number of different ways that we can visualize this. Now, when light reflects off of a surface, we could have all the light rays stay parallel to one another or bounce off in a scattered pattern. And those are two different types of reflection. We have regular reflection and diffuse reflection. Regular reflection is when you could see a mirror image. It usually occurs when it hits a surface that's very smooth. It could be a mirror, It could be a piece of glass, it could be something that's waxed, or any other highly glossy type surface. All of the bumps and grooves on the microscopic level are filled in by the gloss, or in the case of glass, or it's a smooth surface to begin with, and you'll be able to see an image in that surface. Now, when you do that, what's happening is all the light rays are bouncing off the surface and maintaining their integrity in terms of their position with respect to one another. Our brains extend those lines backwards, and we're going to be able to see a mirror image in the object. Now, different types of mirrors can be curved or flat. In the scope of this course, we're going to stick to plane mirrors, so only flat mirrors. On the other hand, instead of regular reflection, where they all stay together and we can see a mirror image, we may have diffuse reflection. And that's any object that you can't see an image in. So a piece of copy paper may have diffuse reflection. Light rays come in, they bounce off in all directions, and scatter. We cannot see ourselves in a piece of copy paper. Now, normally we can't see ourselves, let's say, in the hood of a car. But if we took wax and filled in all those bumps and grooves, we then may be able to see a mirror image in it. So before we wax a car, we may have diffuse reflection. And then when we wax it, we may find that all of a sudden we have regular reflection. But the way you can determine whether or not that's regular or diffuse, if you can see a mirror image in the object or see an image in the object, it is regular reflection. If you cannot, it's diffuse reflection. The key is that all the light rays are still bouncing off at the same angle. Just because the image is scattered and you can't see an image in the surface does not mean that the law of reflection isn't true. The law of reflection is true. However, because of the bumpy nature of the object microscopically, it's going to scatter in many directions. And that's why we would draw a normal line to each actual light ray and then be able to show that the angle of incidence is still going to equal the angle of reflection. So we could have some sample examples of regular and diffuse reflection. But what's important is that no matter what, each light ray still holds true to the law of reflection. Now, you could be asked a little bit about plane mirrors. We're going to stick to plane, which is flat, in this course. We could have curved mirrors, which has a much more complex set of rules associated to it. But when we have a plane mirror, there's a few things to realize. First of all, your brain is going to extend the lines back from the reflected surface of the mirror into the mirror and produce an image that we're going to see. The left and right are inverted. Vertically, the object is still upright, so you're going to have the same orientation. It's going to be the same distance away. So if you're 3 feet from a mirror, your image is going to be 3 feet. So the total distance between you and your image would be 3 plus 3, or 6. You're also going to be the same height. So the height of an object is also the same. Basically, this is because the light rays are traveling in a straight line, and everything is symmetric because of those light rays traveling in a straight line. Curved mirrors do have different effects. So if you have a makeup mirror at home, that may magnify your image. If you have a rear view mirror, that's going to be a plane mirror where it's inside the car. But the side view mirror is curved outward. It's actually convex. And that gives you a bigger view or range of sight so you can avoid blind spots. So curved mirrors, if it's concave, which is bulging away from you, that can cause magnification. So usually makeup mirrors are concave. Convex, on the other hand, are typically side view mirrors, or if they're still using mirrors in stores where they're trying to see the whole store and avoid shoplifters, those would be convex. What you could do is see an object in a convex mirror. It's a bigger view, but it's smaller. So you're going to actually see a smaller image of the objects. That gives the storekeeper a bigger range of view, and they'll be able to see all the aisles in the store. But for our purposes in this course, plane mirrors are the ones we're going to typically talk about. Objects are the same distance away as images are the same distance away as the object. They have the same height, and they are in the same orientation. All of a sudden, you're not upside down in the mirror if you look at yourself in your bathroom mirror. With the law of reflection, every light ray bounces off at the same angle that it started in. So the angle of incidence equals the angle of reflection, and we always measure the angle with respect to a normal line. Typically, this is just geometric, and all you have to worry about is if they give you the angle with respect to the surface, in which case you'll have to find the complement of the angle first. That's all for today, and that's the law of reflection. Thank you. All right, our next topic of discussion is reflection, and we have the law of reflection that says theta I equals theta R, which is the angle of incidence equals angle of reflection. So I is for incidence and R is for reflection. And the way we work with this is as a light ray comes in, it will bounce off and reflect when it hits a surface. Now remember, three things happen at every boundary. We have reflection, refraction, and absorption. So some of the wave will go into the object. So if it's a mirror, some of it's going to go in here. But we're concerned at this point with the reflected light. Now, in order to figure out these angles, we have to draw a normal line. And the angle will be measured between here and here. So this is theta I, and this is theta R. Now, some problems will deal with the surface angles, and that's to trick you. For example, if they say that this angle is 30 degrees, then you know that this has to be the complement. So that would be 60, which means theta I would also be 60. So this is just geometry. Now, other questions will ask, what's the angle between the incident and reflected ray? Well, in that case, you have to figure out the entire distance between them, and this would be 120 degrees. So they could ask it in different ways. Now, you may be asking, why do they make you draw the normal line? So the normal line is how we measure it. But the reason we use the normal line is because not every surface is completely flat. In fact, most surfaces are bumpy in a microscopic manner. So what's going to happen is light ray is going to come in and reflect, and it's going to still work in terms of the normal line, but it's going to be easier to draw a normal line if you have a curved surface. Now, with the law of reflection, we have regular and diffuse. When we have the bumpy surface, it's going to be diffuse reflection. And then when it's off a mirror or really flat surface, it's going to be regular. Now, regular, you can see a mirror image, and diffuse, you cannot. Now, here's what happens. If you have incoming light rays come in, and you have diffuse reflection, when they hit, they're going to all scatter in different ways. So as the light rays come in, they're all parallel. They're going to reflect, and they're not going to break the law of reflection. Each one of these is truly the same incident and reflected ray here. But because the surface is uneven, the light rays scatter, and you're not going to be able to see a mirror image. On the other hand, if you have a flat surface, all the light rays are going to come in, and they're parallel, and they're going to bounce off parallel as well. So what will happen is, if we're viewing this, and your eye is here, the other way, here's your eye, what's going to happen is, your eye will detect this light coming from these organized rays, and your brain extends them back, if it's a mirror, to a common point. So it extends it back to where they meet, and that would be where you view the image. So that's the difference between regular and diffuse reflection. Law of reflection is true for every ray, but if they scatter, it's diffuse, and no image. And if it's regular, you'll see an image. Now, when we're dealing with a plane mirror, what's going to happen is every light ray that bounces off the mirror is going to go into the person's eye who's observing the image. So I'll just look at two light rays. What's going to happen is the light ray from the top of the candle, in this case, is going to hit the mirror and bounce back. But your brain knows Fermat's principle, and it's going to extend a line back on the other side of the mirror until other spots, now maybe like over here, bounce off, and you're going to extend that back as well, and you're going to see the candle's flame here. Well, at the bottom, It's going to hit, it's going to bounce to the eye, and it's going to extend back to the bottom here. So each ray is going to combine in the person's eye, and their brain is going to extend that back. Now this one's probably should be about here, and then that would extend down here. So each of these rays is going to hit the mirror, bounce to the eye extends it back, and you're going to see the image on the other side of the mirror. Now what's important about a plane mirror, although this drawing is not the best, is that the distance from the candle to the mirror is going to be the same as the distance from the image. So this is the image you see, and we call this the object. So the original candle is the object, and the virtual candle in this case is the image. The distance is the same. The height is the same. So it's the same height. You're not bigger or smaller. And you're also upright. You have the same orientation. Now, when we have curved mirrors, things act differently. But for the scope of this course, we're going to stick to plane mirrors, and plane being flat. So all we have to remember is that the distance of the object and the image are the same, although not very well drawn in this diagram. The height of the two are the same, and you have the same orientation, so it looks upright. With curved mirrors, you could have different magnifications. The image can be bigger or smaller. It may be inverted, maybe upside down in a curved mirror. And it may even be on the same side as the object itself. So we have different types of events with curved mirrors and even curved lenses as well. But for our purposes, we're going to stick to plane mirrors. So the distances are the same between the object and the mirror and the image in the mirror. The heights are the same, and the orientation is the same. Now, what I have here is a laser pointer, and we're going to be able to look at the difference between regular and diffuse reflection using a laser. Now remember, regular reflection you can see an image, and diffuse reflection you cannot. Now this whiteboard is fairly flat, so you're able to see a reflection of the laser onto my hand as it bounces off of the surface. Now if we were to trace a line, it would hit here and bounce up to me. And what we'd be able to do is measure the angle by drawing a normal line up. Now the fact that we can see the image on my hand, or the laser point itself on my hand, shows that we have regular reflection. If I take a piece of paper and try to do the same thing, you're not seeing the reflection on my hand anymore. If I move it, you can see the reflection on my hand. If I put it back, you can't. So this is still reflecting, it's just reflecting diffusely. Now it might be easier to see if we have a mirror. As it bounces off, we're getting the same type of reflection that we see off of the whiteboard. So the mirror and the whiteboard are experiencing the same type of regular reflection. Now if I were to hold the mirror vertically and line up the laser pointer, there we go, so that it hits right at that point of intersection, we'll be able to see the light ray bouncing off the mirror. And we can see some reflected light in the mirror as well. But at this point, right about, turned it off, right about here, if I hold it right, there we go, we can see the light ray bouncing off. Now if I had four hands, I'd be able to draw this while it was standing here. Now as it goes, there appears to be, I'll try to draw. I'll draw the light ray in, and then as it bounces out, I'll try to simulate that. It's hard to tell right now, but it looks like it's doing this here. Trace the mirror. And what we have is a situation where if I were to get a protractor, these angles would be the same. Now, of course, didn't use a straight edge for this. Not the best drawing, but oh, look at that right there. It's traveling along the light ray, hits the mirror, and then it bounces off on that same line that I drew over there. So the angle of incidence and the angle of reflection will be the same. I could try to do the same thing with the paper, but we're not going to be able to see that outgoing ray because all the light rays are scattered when it hits the paper. The paper has microscopically a bumpy surface, and it does not produce a mirror image on the other side.